Assalamualaikum. We are Group 11 represented by Tina, Alif, Zul and Sarah. Today, we present our analysis of building electricity demand patterns across 2017. Power distribution networks face major challenges when handling peak loads. By studying power consumption around a mid-year seasonal shift, we can better understand baseline demand trends and optimize building energy efficiency.
Okay, now moving on to the engineering problem and objectives. When weather change, cooling system work overtime. This causes sudden spikes in power usage that put heavy stress on the electrical grid. The main issue is that the old management systems use simple historical average, which means how much heat builds up in a modern glass buildings. To solve this, our study has two main goals. First, we want to check if power usage move up in a big way between the first and the second half of the year. Second, we want to test how much outside heat directly drives total power demand.
So next, let us look at our dataset. We obtained our data from Kaggle titled powerconsumption.csv. The dataset contains 52,416 hourly observations recorded throughout 2017. To analyze seasonal changes, we divided the data into two equal periods at July 2nd, Group 1 before the shift and Group 2 after the shift, with 26,208 samples each. The primary variables analyzed include timestamps, power draw across 3 building zones, total power consumption in kilowatts, and outdoor temperature in degrees Celsius.
Moving on descriptive statistic, let's look at the baseline shift in building electricity demand before and after the mid-year mark. Looking at the numbers, our average total power consumption increased by over 4,000 kilowatts, rising from 69,210 kilowatt in Group 1 to 73,235 kilowatt in Group 2. But the shift isn't just about higher average usage. It's also about higher volatility. The standard deviation expanded from 15,588 kilowatt to over 80,348 kilowatt in the second half of the year, and our peak demand surged from 111,000 kilowatt to a massive absolute maximum of 134,208 kilowatt. With a balanced dataset of over 26,000 hourly observations in each group, this descriptive spread clearly indicates a heavier, more unpredictable load on the building's electrical system.
Building on the methods we just discussed, let's look at what the visual data show us. If you look at the daily average plot on the left, you can see a clear mountain shape that peaks right in July and August. This matches the hottest months where energy usage reached its highest levels. Next, the box plot shows that in the second half of the year, energy demand shifts way up. We even see extreme spikes going past 130,000 kilowatts. Finally, the yellow histogram shows an extended tail on the high side. This confirms that the building spends much more time running at high power levels during the warmer season.
So moving on to hypothesis testing. To confirm whether this load surge was statistically significant or just a random variation, we conducted an independent two-sample t-test on this slide. Our null hypothesis stated that there is no difference in mean power consumption before and after the seasonal shift, while our alternative hypothesis proposed a significant difference. Setting our significance level at 0.05, the test yielded a t-statistic of negative 27.07 and extremely small p-value of 3.2 times 10 to the power of negative 160. Because this p-value is far below our 0.05 threshold, we conclusively reject the null hypothesis. This confirmed that the sharp increase in electricity demand across seasonal boundaries is statistically significant and driven by underlying environmental changes.
So now, we analyzed how outdoor temperature impacts power demand using linear regression. The scatter plot on the left displays all 52,416 data points with a fitted trend line. Using mathematical formulas, we obtain a slope of 1,439.25 and an intercept of 44,150.51, resulting in our regression equation, which is y is equal to 1,439.25x plus 44,150.51. This leads to two key engineering insights. First, sensitivity. For every 1 degree Celsius rise in outdoor temperature, total power demand increases by 1,439.25 kilowatt due to increased air conditioning usage. Second, model fit. Our R-squared value is 0.2384. This shows that outdoor temperature alone accounts for nearly 24% of the total variation in building electricity demand.
Okay, now let's see how these findings connect to real-world engineering and sustainability. First, our line equation shows that for each single degree Celsius bump in outside heat, building power demand climbs by almost 1,440 kilowatts. Facility teams can use the exact link to set smart cooling schedules, saving money and keeping systems safe. Second, by managing these heat peaks, we support UN Sustainable Development Goal 7 for clean energy by cutting down on expensive backup power plants. Lastly, this data helps city planners build automated microgrids under SDG 11, helping transform basic towns into smart, sustainable communities that can handle changing climate conditions with ease.
So to conclude our presentation slide, our statistical analysis confirms that building energy profiles are heavily influenced by seasonal transitions. Our regression analysis show that ambient outdoor temperature alone accounts for nearly 24% of total power volatility, with every single degree Celsius increase adding over 1,400 kilowatt in mechanical cooling demand. For engineering practice, these findings provide data-driven justification for facility managers to optimize HVAC scheduling, manage peak grid strain, and implement dynamic load shedding protocols. Moving forward, extending this model to include relative humidity and occupancy rates will allow us to build even more precise predictive tools for sustainable energy management. Thank you.